no idea whose number that is. It's not mine. So I'm assuming whoever's it is will write it up again if he or she needs to. My number's in the syllabus, and so I think the extension is 3376, but I so rarely call my office. I don't have, not 100% confident. All right, so let's start out with, this is Physics 152. I hope all of you are aware. Not to see any look of fear in anyone's eyes, but we're good so far. Whether you call me Dr. Fox or George or something, the title is Doctor, so if you're going to go with title, please put Doctor, not Mr. That's my brother. Depending on how I feel, I might harass you about that. My office is Ardmore 256. So, for those not familiar with it, if you walk up the steps in Ardmore, then if you go to the right, that's where the classroom is going to be. If you go to the left, go down that hallway, go down the next hallway, and just before the emergency exit, there's a door on the right with a big green dot on it. That's my office. Or if you're in my class, or if you're in the physics room, my office, there's an adjoining room, and you can just walk in that way as well. And the only thing that you potentially have missed was that I'm looking at potentially a different room for the class. It will not be in the physics room because Physics 252 is in there right now. So unless we want to start picking them off one by one, we will not be in that room. Have any of you watched the course roadmap? It's been available to you for 3 hours now. In the course roadmap, I start with basically where we're going to be at the end. Potentially we're going to get farther, it depends on the pace of the class, how many questions are asked and things like that. But to date, I've gotten as far as sort of the beginning of that, and I work backwards. And at the very beginning of it is charge. And that's sort of the starting point for the entire course. And we've got a bright intellectual group here. Somebody tell me what charge is.
The amount of electrons on a particular object.
Say it again.
The amount of electrons on a particular object.
Man.
The amount of electrons on a particular object.
Oh, amount of electrons on a particular object. Why?
Electrons can move freely, unlike photons.
What do electrons have to do with charge?
They have a negative charge.
Then what's charge?
The atoms.
Well, you said electrons have charge, so apparently it's more than just the atom.
Oh yeah, the protons have positive charge.
Well, it's the charge. Then what is charge in general? Not just the charge of an atom, charge in general.
How many protons versus? I'm not sure.
Then you're still going down to looking at the atom, I think.
Yes.
All of you have had chemistry of some sort. A couple were less confident when they made a gesture just then. All right. I assume most of you have heard of charge before. And they talk about electrons being negatively charged and protons being positively charged. And someone will probably even go to the next step and tell you what the charge actually is. I can't remember in chemistry whether we were ever told that, but I assume we were at some point. But did they ever explain what charge was?
It's like an attractive or repulsive force.
The charge itself is not the force. It causes a force. Good news, there's going to be an equation involved.
Yeah, what is the definition of charge?
One of the reasons why you're having difficulty and why you went to the electron-proton bit is that's basically how it's introduced. Coming up with a formal definition of charge is not easy. It seems to be there's this property of materials such that which will cause a repulsion or an attraction, so they cause force. But what charge is in and of itself, we're not 100% sure. but we're gonna pretend like we know what it is. So it seems to be a property. And these markers, who knows how long they've been sitting there.
You didn't throw it on the floor.
I know,
It's not the same though.
it's not. I guess it'd make more noise when I throw it this time. So it's a property. Ooh, my handwriting's gotten worse over the past several weeks. Or some of you might be looking at that going, no, it's pretty much the same. And I'm gonna use a vague term like object, property of objects, or of an object. Which can cause attraction, repulsion, or neither. And you probably can make an easy argument for both, but I'm not gonna leave that one out for now. So we have this really vague thing that we're gonna be working with throughout the semester and looking at sort of what are the implications of this property. And if it seems strange to start out with just saying, hey, our foundation of our entire course is nebulous, think about time also. Time is also incredibly difficult to define, but it is the basis of a whole lot of what we do. We seem to have some intuitive idea of what it is, but actually if you wanted to formalize the definition, it's not easy. Especially since time is not the same for everybody, and that's what we'll be hitting at the end of the course. All right, so what do we know about charge? You mentioned electrons and protons. What do we know about charge and those things?
Attraction and repulsion.
Okay, when is there going to be attraction and when is there repulsion?
Opposites attract. So if there's, I think of magnetism a lot when it comes to charge. So if you have,
Yeah, be careful about that one. I mean, the generalization you just said works for both of them, but I've seen students run into issues later on because they think about, when you think about the direction of an object's going to be forced, it gets more complicated than that. So rule number one though, opposites attract. And consequently, like repel. Alright, I'm guessing Daniel and Harrison, you two are the farthest away. Can you read this, okay?
I can, yeah. I just had to move from the.
If you need to shift that, not onto the floor preferably.
Okay.
Or if it's onto the floor, not fast. But if you need to move it, feel free.
I'll move it, yeah. Oh, that's heavier than I expected.
do you want to?
Sure.
Thank you for not dropping that.
Yep.
I'm assuming the table is sound.
I hope so.
It's not even wood around here. I guess it worked out. All right. So rule number one, opposites attract like repels. And with electrons and protons, which one are the negative, which one are the positives?
Electrons are negative, protons are positive, and then you have neutrons, which are neutral.
All right, so an electron, because that's just too much to write, we have an abbreviation for it. Let's just E with a little negative sign. Proton, equally clever, P with a plus sign. And then neutron, which is not really much, we're not gonna do a whole lot with neutrons, but just for pretending atomic completeness, N with a 0 there. And of course, charge is too much for us to write, so we need a letter for that one also. Depends on how you want to look at it. We have a letter or two letters, depends upon what you want to call it. But the letter Q is traditionally used for charge, and this is traditionally a single charge, or capital Q for a collection of charges. Now, it's not so hard and fast that if you were talking to a physicist and you use the lowercase q for a collection of charges, they probably would not care. But textbooks tend to use lowercase q for a single charge and capital Q for a collection of charges. What do you know about the charge of an electron versus the charge of a proton, besides being opposite signs?
Are they equal in magnitude?
They are. Now, you say equal in magnitude, the absolute value is equal. Charge is a scalar, so there's no direction involved in the charge itself. And so if you think about magnitude as just being the absolute value of it, and the sign tells you a direction, the sign is not telling you a direction here. The sign is the actual label that we assign to it. And so, because these have opposite charges, magnitude is the same, or absolute value is the same, we, of course, have an abbreviation. Why not? So we use the letter E to represent that base charge, what was at the time considered a fundamental charge. So it's roughly 1.6 times 10 to the negative 19th coulombs. And anyone want to take a wild shot at for whom it's named?
Some old white guy.
I missed what, Anna, what did you say?
Some old white man.
Yeah,
It's not
European
that
also,
space.
you can go with that typically.
Yeah.
Although we do start to learn, there is a electrical unit called the Franklin, so we actually, our first unit named after an American, I think we would have dealt with.
This is the formula for.
This is the value for the base unit of charge. At this point, theory has that there are things with smaller charges than that, fractional, what sometimes called fractional charges, quarks, for example. Some quarks have a 2/3 value of that, some quarks have a 1/3 value of that. All right, so we can now take these symbols that we have here, and of course, we want to write as little as possible. So I can say that the charge of an electron is negative E. The charge of a proton is positive E. So right off the bat, within the first couple of minutes, we have two different E's here, which mean two different things. This E right here is for an electron, this E right here is for the actual value of a charge. There's one more E that you would have potentially seen in math class. Oops, lost it. I think it's 2356, but I'm not 100% sure of those last four digits.
Isn't that natural law?
That's the one right there. So now we have three different E's here, all meaning different things. Later on, we're going to use the letter mu, and mu is actually going to represent 4 or 5 different things. So just because it's the letter E doesn't mean it's going to mean what your first gut feeling is. Hopefully it will.
At least it's not K. We're done with K.
We're about to come. We will have a K potentially before the end of today.
All right.
All right. Questions up to here?
So this is not necessarily like just electricity. This is all encompassing, correct? Like charge and whatnot. Because when I think charge, I'm thinking like electricity inherently.
Yeah, I always find electricity to be also difficult to formally define.
Oh yes.
It's like gravity.
Got it.
It's like electricity is a huge topic of which we're looking at parts of it.
Oh, okay.
So yeah, charge is something that will be throughout the course. at some point it will be disguised, but it's still there at the heart of it.
Got it.
Did I address what you just asked?
Yes.
Okay. Rule number 2. Charge is conserved. That's something you potentially got in chemistry. If I have two objects that are a net result positively charged, it will always be. So if I've got something with let's be more specific. I have an object here with a charge of -2 units and a charge here of +1 unit. If let's say that they're conducting metallic spheres, well, conducting spheres, I've got this charge all over the top of them. I touch the two spheres together, and charge gets transferred. What will be the net charge of them after they touch? The total charge.
-1?
Absolutely. Because whatever the charge is being transferred from one object to the other, and ultimately this, if they're really good conductors, -1/2 unit and -1/2 unit, they would balance out. There's some other factors involved, but it's good enough for now.
So if these two spheres hit, and this one was -2 and this one was +1, it would end up being -1/2 and 1/2?
Yes, if they were touching for, a second or two.
Okay, so to get that, you would subtract 1 from -2 and then divide it by 2. Like to get the,
Or add 1 to -2.
yeah, sorry.
Yeah,
Alright, sweet,
because the net charge is gonna stay the same, and so it's split evenly.
right.
Forget something here. Rule number 3. Plus. Within your world, unless you get into potentially high energy physics or into some really, probably certain specific branches of engineering, 99+% of the time, electrons move. Not the protons. Or neutrons, but we really don't care about them. So I have a piece of PVC right here. It is what I'm going to assume is negatively charged, or neutral. I have rabbit fur here. We will assume neutral. And we can sort of have more of a guarantee that it's neutral just by touching it against something that will conduct any excess away or add to it. If I rub them together, this should be now charged. And let's pull out the straw, see if this demonstration actually will work. It is physics after all, so who knows? Apparently my hands are charged. So it did cause the straw to turn, and I assume this is not on video, but. All right, so this I assume is still charged, we'll find out. As I bring it close to the straw gets repelled. So, what conclusion can we draw, first off, about the charge of this and the charge of the straw?
They're the same,
Yes.
because it would repel that.
Okay,
Did electrons move?
did they?
Great question.
Now,
Now, was the straw neutral to begin with?
no, it was negative, but also when you took off the paper, it probably transferred some negative
Right.
charge to the straw itself.
So what would happen if we neutralize the straw? Fortunately, there's a metal sink here. I guess one advantage to this room. Now it's possible to pick up some trace amount of charge from me. Oop, apparently. That could have been some other force there. All right. Let's neutralize this. Please work. Ooh. There's some of these things that occasionally have to get washed just because they start getting oils from hands on them and things like that. Hoping that's dry enough. All right, so if I bring it closer, what's gonna happen? Nothing. All right, so can we agree that at least one of them is neutral? Actually, they should both be neutral. So if that's neutral, and this is charged now, how did that move?
Are electrons moving to the straw to repel it?
Oh, as in electrons jump from here to there?
Yeah.
Did you see or hear a spark?
No, I did just then. That was just
Oh.
like static electricity. So.
So if the electrons did jump, that's what we call a spark.
Okay. That did not happen.
And it's that time of year where you get to experience it more and more. So why, if the straw is neutral, I'm assuming that there's nothing jumping. If any electrons do jump across that space, it would be a very small number, not significant. So how is it that that gets repelled if that's neutral?
One is charged.
Pardon?
One is charged.
Yeah, but that's neutral. We had the rule of opposite track like repels, but what about neutral?
Like, it doesn't have to be charged, does it? Just as long as one of the objects.
How does that work? How can a neutral thing be repelled or attracted to a charged thing?
I want to say if it like gets electrons and then like somehow becomes charged that way.
Have any of you ever rubbed a balloon on your head and stuck it to a wall?
Yeah.
Yeah, so they're not electrons